how can we use this thing to our advantage? A is moving like this with acceleration A, B is moving like this with acceleration B. If two bodies are connected as shown. Hello everyone and welcome to LN Overseas. So I'm back with the series that is 45 topics in 45 days. In this series we take 15 topics from each of the subject, of course summing up to 45 days, 45 topics. And today we are going to take a topic of physics, and that is the constraint motion, right? This is a concept from kinematics. And when I talk about constraint, constraint means to restrict. So if I am holding any object, I am constraining that object to my hand. So constraint as in I am not allowing that object to move, right? So this pen can only be moved if I am going to move my hand. Getting the point? Yeah. So it cannot move by itself. So I have constrained the motion of this pen. So relative to my hand, this pen is constrained. Yeah. So here we are going to talk about a little bit of common sense, nothing more than that. So let us begin. Arch your back, take a deep breath. When we talk about constraint motion, there are two important constraints that we study in our curriculum. Those are string constraint and wedge constraint. String and wedge. So let us consider the string constraint first, right? Okay. Now here consider any two objects that are connected by a string, and my complete discussion is going to be based on the fact that the string is first of all massless, right? That's the general consideration we always have. Second, it is inextensible. Inextensible. This is important, that the length of the string is not changing at all no matter what, right? Okay. So this is the fact I will be using, and there is one more thing that we always have to remember, that this string is always tight, right? The older way is taut, T-A-U-T, taut, right? That is the older version of tight, right? Opposite of slack. Okay. So the literal thing we will be using is inextensibility of the string. How can we use this thing to our advantage? Nice question. I'm glad you asked. Okay. So suppose you have this block, right? M2 and M1. Suppose M2 is moving with velocity V2, right? And mass M1 is moving with velocity V1. Then you must agree that V1 must be equals to V2 if the string is inextensible and it does not slack. Agreed? Yeah, that's common sense, right? That means if this thing moves 2 meter, this thing also moves 2 meter in same time. Simple. That means if the velocity of this point is V1, velocity of this point will also be V1, for this point it is also V1, for this point it is V1, for this point it is V1, and hence V2 is equals to V1, right? So if the velocities differ, then the string will become extensible, then the strings are going to extend, isn't it? Yeah. So if strings are going to extend, or they could break as well. So if the velocities are different, they could break, but that I'm not letting that happen, right? I said that the string is inextensible. So that means that the velocity along the string is constant. Yeah. Nice. Or more correct word is same, right? All along the string. Okay. How to get this mathematically? Suppose x2 is the displacement of this block, x1 is the displacement of this block, right? and I'm saying length of the string is constant. Suppose length is L, right? So let us mathematicize it, right? We have a literal statement that the string is inextensible. So length is constant. This is the mathematics. Okay. Now what? What I can infer from this? Differentiate this thing, right? So the rate with which the length is changing, right? This thing is equal to constant. A constant is a 0, right? Differential of constant is a 0, right? I will be writing this thing as L dot, right? This is a Newtonian shorthand generally we use for differentials. So that is L dot is equals to constant. So this is the rate with which length is trying to change, right? It is not changing. Okay. So look here, V2 is trying to extend the string, trying, right? So if this is the string, V2 is trying to extend the string and V1 is trying to decrease the length of the string. Getting it? V2 is increasing the length, V1 is decreasing the length. So the rate with which the length is increasing or decreasing, right? Let us say increasing. This thing is going to be V2, right? Or say plus V2. Why? Because it is increasing, minus V1. Why V1? Because it is trying to decrease the length. This thing must be equal to 0. That means V2 is equal to V1. We knew it. We knew it from common sense that V1 must be equal to V2, and this is how we use mathematics to prove the same thing. Why we require mathematics if common sense works? Right? Because if we take the complex system, then common sense is going to be null and void, isn't it? Yeah. So basically, at the end, what is the final conclusion? That I will be taking length is equals to constant and I will be proceeding from here. Agreed? No rocket science. Yeah. So let us take a question. Find the constraint equation. So constraint equation means I have to relate the velocities and acceleration of the blocks, right? So there are certain series of steps that you must follow in order to actually get the constraint equations. So first of all, step 1, count, right? Count or number the strings and objects, right? So let us count the strings. How many strings are there? So we have first string that goes something like this, from the through the pulley goes something like this to this point. Yeah, nice. This is the first string. What about the second one? The second one will be something like this. This is the second string. So we have first string and the second string. Nice. Now we have two objects, first object, second object, and I am saying that this pulley is movable. So this is my auxiliary object. Auxiliary object, right? I have to eliminate the movement of pulley because I have to relate the motion of M1 and M2 only. Pulley is moving, that's a fact, and that is why I am considering that that is a third object, but I have to eliminate the parameters related to the pulley. Okay? So what's the second step? What we did in the first step, we numbered everything, we counted the strings and we counted the objects. Second step is assume variables, right? Variables of motion. So it could be displacement, it could be acceleration, it could be velocity, right? Let us talk about velocity. Now we have to assume It is up to me that in which direction I will be assuming. If I get a negative answer, then definitely my assumption is quite opposite. Okay. So suppose this is moving down, this thing is moving down, this thing is moving down with say velocity v2, and this thing is moving up with velocity v1. So how do you know? Assumption, assumption, my free will. Okay, well and good. Now I am saying that this pull is also moving. So suppose this is moving down with velocity vp, velocity of pulley. So we have to relate v1 and v2, eliminate vp. Okay. Okay. Now third, write all the lengths, right? Write all the lengths. So let us see how many lengths are there. So suppose the length between this point and this point, right? That is the instantaneous length. That is L1. Agreed? Next, this thing is L2. This thing is L3. And this thing is L4. This is first length, second length, third length, fourth length. These lengths can change, but the overall length of the string is not going to change, right? Write the lengths. Second, write the constraint condition for each string. For each string, write the constraint condition. So take first string, right? String 1. For string 1, the complete string looks something like this, right? This yellow one. Okay. So let us calculate the complete length of the string. So length of the string, first L1. Suppose the radius of the pulley is R, right? Suppose, could be anything. Plus pi r, right? This length pi r plus L2 plus pi r plus L3 is equals to 0. Check. Yeah. Right? Not 0. Constant. Right? This is constant. The length of the string is constant. This is the complete length of the string and that thing is constant. Okay. Can I write it like this? L1 plus L2 plus L3 is equals to C minus 2 pi r. Yeah, pi r plus pi r, 2 pi r, take it to the other side. Pi is constant, radius of the pulley is constant. So this thing is also constant. So this is again a constant C only. So the final result that I was seeking is L1 plus L2 plus L3. This is a constant. No rocket science. Now what we have to do? You guessed it right. Absolutely. Differentiate this thing. So L1 dot plus L2 dot plus L3 dot, this thing is equals to 0. Yeah? No rocket science. Next. What is L1 dot? The length with which L1 is changing, right? Or the rate with which the L1 is changing, right? So V1 is trying to decrease the length. Trying to decrease the length. So what will be L1 dot? L1 dot? It will be minus V1. Agreed? Decrease the length. What about L2? Right? This is L2 dot. L2 dot is the rate with which L2 is changing. Vp is the velocity on the other end. Here again there is no velocity, right? And Vp is trying to increase the length. So plus Vp. And what about L3? Again Vp is downwards, right? Velocity of pulley is downwards. Again velocity of pulley is trying to increase the length L3. So for L3, or the rate with which L3 is changing, is Vp plus Vp. And this thing must be equal to 0. So from here, V1 will be equals to twice of Vp. This is the first equation, first relation that we have, right? Yeah, first relation. So what was it? V1 is equals to 2 Vp. Now let's talk about L4. L4. So L4 dot is equals to 0. Do you agree? L4 is equals to constant and L4 dot is equals to 0. What is L4 dot? It is the length with which L4 is changing, right? So M2 is going downwards with velocity V2. Pull is also going downwards. So V2 is trying to increase the length. Vp is trying to decrease the length, right? So V2 increase minus Vp decrease. This must be equals to 0. So V2 is indeed equals to Vp. Again, that's something I can definitely say from the common sense, right? V2 is equals to Vp. We had the first equation, V1 is equals to 2 Vp. Substitute the values. So V1 is equals to 2 V2. That is the relation that we were seeking. So if this is true, differentiate this thing. So A1 will be equals to 2A2. That is also a fact. Integrate this thing. X1 will be equals to 2x2. That is also a fact. Right? So these are the constraint relation that we were seeking. Same, no rocket science. So this looks overwhelming. Yeah, but you will get the gist, right? When you are going to try it by yourself, you get the gist. Can this thing get better? Actually, it can. Actually, it can. We can use a simple concept from work energy power, right? So if you have learned work energy power, by now you may be getting this concept, okay? Now, we very well know that there are only conservative forces acting, right? So we have an ideal pulley that is massless and frictionless. So frictionless, friction is absent, so it is only conservative force. Okay. So for the complete system, if I ask you, what is the work done by tension? For the complete system, I am saying. Sir, for the complete system, work done by tension is 0. Yeah, that is 0. Work done by tension is 0. So how can we use this to our advantage? Okay, let me tell you. So if I have to write work done by tension, that means T dot x, right? T dot x must be equal to 0, right? And T dot x is on the complete system. That means if tension is acting, right? If tension T is acting all around the system, then T dot x must be equal to 0. That means whatever the tension is doing to this block, it is doing exactly the opposite to this block. Opposite. So we have to talk about the net tension. So I am writing summation here. So work done by tension on this block plus work done on tension on this block, this must be equal to 0. For any individual block, it is non-zero. For complete system, it is absolutely 0. So if this thing is valid, then you may say that the power delivered by tension is absolutely 0. Yeah. And if this thing is valid, that means T dot A must be equal to 0. Right? T is the tension force. Yeah. So let us first calculate the tension in the string. Suppose the tension here is T, right? It is the same string, massless string. Again, tension here is going to be T. Tension here is going to be T. No rocket science. If it is a massless pulley, then the complete force will be transferred. So tension here will be T plus T. and it will be 2t. Agree? Yeah. So again, let us assume the velocities. This is going down with velocity v2. This is going up with velocity v1. Right? So from here, let us use this relation, power delivered by tension must be equal to 0. What is the power delivered by tension on this block? That is T into V1, and both are in the same direction, cos 0, right? This is a dot product, work done is a dot product, cos 0 plus second 2T V2. And now what is the angle between tension and V2? Tension is always away from the object. So this is the tension that we have to consider. Tension is like this. Tension is like this. And velocity is downwards. What is the angle? 180 degree. This must be equal to 0. Can I cancel T? Throw it to the other side? Definitely I can. Cos 0 is 1. So V1 plus 2V2 times minus 1 is equal to 0. Cos 180 is minus 1. So V1 is indeed equals to twice of V2. That is the relation that you can definitely get from this method. Right? This method has a name, that is the virtual work method. So what we were using? We are using the fact there are only conservative forces are acting. So the complete work done by tension for the complete system is absolutely equal to 0. From that fact, we have written one equation only and we have a result. Okay? No long procedure. Yeah. Moving ahead, let us take another example. Right? Find acceleration of block C in ground frame. Ground frame. Okay. So A is moving like this with acceleration A, B is moving like this with acceleration B. And suppose C is moving like this downwards with acceleration AC with respect to A. Now I am sitting on A observing C. Right? This is acceleration of C with respect to A. Because if it is moving downwards, A is moving towards right. So A is taking C along with itself when it is moving. That is what going to happen in the ground frame. So this is AC with respect to A. So that's how we have to get ACA. So consider the complete system. Let us use the virtual work method. You can use the first method as well. Calculate the tension. Suppose tension here is T. Same string, tension here is T. Same string, tension here is T. Same string, tension here is T. Okay? Nice. What I can use? Summation of T dot A is equals to 0. Only conservative forces. Yeah. So what is the tension? How many tensions are acting on block A? This is T plus T. T plus T, right? This T is trying to pull A in this direction. This T is trying to pull A in this direction. So T plus T, 2T. Net tension. So 2T into A cos 0. Cos 0 because it is in the same direction. What about B? Plus 2T, again 2T. Why 2T? This T is trying to pull B. This T is trying to pull B. Right? 2T. 3 plus T, 2T. Times B. Again cos 0. Why? Because tension is in this direction. Acceleration is in this direction. Right? Okay. What about C? Tension is upwards, acceleration is downwards, and only one tension is acting. Right? So plus T dot or ta c with respect to a cos 180, this thing is equals to 0. One equation only. Can I take t? Can I take t and throw it to the other side? Yeah, I can. Cos 0 is 1. So 2a plus 2b, this thing is equals to, this will be minus c, right? Cos 180 is minus, this thing is equals to a c with respect to a. And that is in the downward direction. So our assumption is correct. We have taken it downwards, so our assumption is correct. Okay. So this is acceleration of c with respect to a, but they are asking us in the ground frame. The ground frame. So c is moving like this as well with acceleration a, because a is moving in here with acceleration a. So in ground frame, right, if this is my ground frame xy, what will be the acceleration? Acceleration of c with respect to ground will be equals to acceleration of a with respect to ground plus acceleration of c with respect to a, right? So this thing is equals to acceleration of a with respect to ground is a I cap. A I cap. And this is downwards, right? We have considered our acceleration downwards, so it will be minus j cap. Getting the point? Plus twice of a plus b. Twice of a plus b minus j cap. That is your result. Right? So this is the acceleration of c in ground frame. No rocket science, easy stuff. Yeah. The next thing is, can you get this using the complete method, the constraint method, common sense method? So this is L1, this is L2, this is L3, this is L4. Please try it yourself. L1 plus L2 plus L3 plus L4 is equals to constant. Differentiate this thing twice. Why? Because we have to work in acceleration. So differentiate this thing is in 2 times and you will get the acceleration relation, and try to substitute the acceleration, and then you are going to get the gist of the complete method. Agreed? The next part of the constraint motion is the wedge constraint. Wedge constraint means if two bodies are connected as shown, right, the objects are rigid. First assumption is the objects are rigid, and the second is the block and wedge are always in contact. So they are moving such that the block and the wedge is always in contact. So you must agree that if they are moving together, so the common sense is that whatever will be the velocity that is in this direction, perpendicular to the interface, that is same for both the blocks. Common sense. This surface here, that this is interface. This is interface. So if this block is moving like this with velocity say v1, and this has moved somewhere with velocity v2, right? So there will be one component of v2 that is in this direction, that is v2 cos theta. Agreed? This is theta, so this is theta. And there will be one component that will be in this direction, that is v2 sin theta. Agreed? And if they must always be in contact, that does mean that v1 must be equals to v2 sin theta. Right? The block could move in any direction, right? It could have any velocity in any direction, but the component that is along the perpendicular direction of the interface, that component must be equals to the component of the incline in the same direction, right? So what we have to do? The perpendicular velocities to interface are equal, right? So in the string constraint, we had a literal meaning that the length of the string is constant. Here we have the literal meaning the perpendicular velocity to interfaces are constant. So let us apply this thing to a question. A plank of mass m rests symmetrically on the wedges B and C, right? So this is wedges B and C. Find the acceleration of plank if acceleration of each wedge is A, right? So acceleration of each wedge is capital A, something like this. So we have to find the acceleration of mass m. So what is the basic sense you get from here? When I am going to release this system, this plank is going to go down and the wedges are going to open up. Simple. So suppose the acceleration of this plank is A, downwards, small a downwards. Easy. Let us make the FBD and try to get the equation. For plank, how many forces are acting? Let us see. First, the most basic force mg. Second, you have normal reaction like this, and this normal reaction will be exactly equal to this normal reaction. Symmetric system. Now if this angle is theta, angle of incline is theta, so angle between lines is angle between their perpendicular, so this is theta, this is theta. So this thing will be equals to n cos theta, this will be n cos theta, right? And this thing will be equals to n sin theta, n sin theta. So along x direction, if I write the equation, right, no other forces are acting. N sin theta minus n sin theta doesn't make any difference, right? It is in equilibrium, right, in x direction. What about y direction? For y direction, which is important because acceleration exists in y direction. So mg minus 2n cos theta, right? N cos theta plus n cos theta must be equals to what? ma. First equation. Okay, nice. Next, what is the first equation? mg minus 2n cos theta is equals to ma. Acceleration of these two is a. So if I make FBD for this m, normal reaction will be acting like this, right? For this wedge only, right? It will be same for both. And mg will be acting downwards. There will be normal reaction acting upwards. Say that normal reaction is n dash, right? Any other forces? No. Resolve n. Resolve n. So if this angle is theta, this angle is theta, then this thing will be equals to n sin theta, and this thing will be equals to n cos theta. Again, no acceleration in y direction, so you can write the equation in y direction, but it is in equilibrium. Y direction is in equilibrium, nothing to worry about. Let's see what's happening in x direction. So I can write n sin theta is equals to ma, right? N is equals to ma by sin theta. Simple. Now, if we talk about these two equations, right? This is the first equation, this is the second equation. How many variables are there? Count how many variables are there. First, there is a, there is a, there is small a, and there is n. How many equations we have? 2. Getting the problem? How to get the third equation? Absolutely correct. That is the wedge constraint. So if this is moving down with the acceleration a, right, and this is moving right with the acceleration capital A, so what will be the component of this acceleration in the perpendicular direction? Sir, if this is theta, this is theta, so this will be a sine theta, right? What about this? So if this is theta, angle between lines is angle between their perpendiculars. So this is a cos theta and this is a sine theta. What does our wedge constraint suggest? That the perpendicular component must be equal. So a cos theta must be equals to a sine theta, or a is equals to a tan theta. So this is the third equation that we require in order to solve this question, right? So from here, substitute the values. We have to find small a, right? We have to find small a, remember. So substitute value of capital A in equation number 2. So n is equals to m, capital A will be equals to a by tan theta. Agreed? Okay. Now we have this equation, we have the value of n. Substitute n here. So mg minus 2ma tan theta, open tan theta, sin theta by cos theta, so this will be sin squared theta into cos theta, and there is one more cos theta here, right? This thing will be equals to ma. So from here, mg will be equals to ma plus 2m cos squared theta over sin squared theta into a, right? Or a from here, if you take out common, this will be equals to mg divided by m plus 2m cos squared theta by sin squared theta is cot squared theta, right? And this is your required acceleration, right? If they ask you for capital A, substitute this value here. You will get capital A. Divide this thing by tan theta. Getting the point? So interesting. Now we can get this from one more method. What's that method? Suppose this is a triangle. This is theta. And suppose this plank is slipping downwards. So if this has a displacement of y in downward direction, so the wedge is going to go towards right xa. So from here, can I write tan theta is equals to y by x, or x tan theta is equals to y? Differentiate this thing twice, x double dot tan theta is equals to y double dot, acceleration. So x double dot is the acceleration of wedge, because wedge is moving towards right, right? So a tan theta is equals to y double dot is the acceleration of the plank, right? Acceleration with which plank is going down. So this is a. So you can get the same thing from simple geometrical tricks as well, right? But the thing that you have to remember, the perpendicular component to the interface, that thing is absolutely same for both the objects. So that's all about the wedge constraint, and that's all about today as well. So it was really nice being with you all, and you can check out the complete playlist in the description box below. And if you have any queries, any discussion, any questions, you can drop them in the comments. And bye bye, have a nice day.